Color centers in diamond are attractive building blocks for technologies in quantum information and quantum metrology. They are atomic-sized defects in the crystal lattice, which introduce local molecule-like electron orbitals in the bandgap. Diamond has a large bandgap, which makes it optically transparent, but electrons in the defect orbitals interact with visible light and give the crystal color. We have investigated a color center in diamond called the silicon-vacancy center, which has gained attention due to its exceptional spectral properties. 70% of its fluorescence is concentrated in a strong zero phonon line, and a weak phonon sideband extends for 100 nanometers.
We have shown that it's possible to identify which silicon isotopes is contained in a single silicon vacancy center. This information comes directly from the fluorescence spectrum of this defect and has enabled us to reliably identify a local vibrational mode of this defect. Not only gives this insight of the physics of the silicon vacancy center, but it's also possible to determine a silicon-29, which gives access to the nuclear spin.
The defect consists of two adjacent lattice vacancies, one of which is filled with a silicon atom. Since silicon is much larger than the carbon atoms of the diamond lattice, it is conventionally accepted that this configuration relaxes to place the silicon in between the vacant lattice sites. We measured the fluorescent spectrum at a cryogenic temperature of 8 Kelvin for 817 individual silicon vacancy centers. At low temperatures like this, the zero phonon line is resolved into 4 fine structure peaks. Most of the centers produced spectra which essentially overlapped. However, about 4.8% of the silicon vacancy centers gave spectral features noticeably shifted to longer wavelength. Another 2.9% of centers were shifted even further. These percentages closely match the natural abundance ratios of the silicon-28, silicon-29, and silicon-30 isotopes. The silicon isotope contained in an individual silicon vacancy defect can thus be determined by the spectral position of its zero phonon line. The only other feature which we found to shift with silicon isotope was the sharp peak at 766 nanometers. This corresponds to a phonon energy of 64 millielectron volts, and the energy decreased slightly as the silicon mass increased. This relationship followed the simple harmonic oscillator, where frequency or energy is proportional to the inverse square root of the mass of the silicon atom. The vibration must therefore be localized on this atom. Previous measurements of the polarization of this 64 millielectron volt phonon peak allow us to be confident that the vibration involves the silicon atom moving along the symmetry axis of the silicon vacancy center. Interestingly, the presence of a local vibration suggests a plausible origin of the measured isotopic shift of the zero phonon line for the first time. Being able to identify the silicon isotope contained in individual silicon vacancy centers is of interest for quantum information applications, since only the silicon-29 isotope has nuclear spin. Nuclear spins in diamond are weakly coupled to their environment and generally have long coherence times, which are necessary for storing quantum information.